All right, APL class, we are going to finish up the notes for the implicit differentiation section, 2.5C, I believe is what we're calling it. And as part of that, as a kind of an extension, logarithmic differentiation fits into this pretty well, because in order to use that, you have to know how to do implicit. So this is kind of an extension. And it is a technique that is very helpful with certain expressions. So example 6 says, how many of the following derivatives can you answer correctly? So these are good to look at. Now this first one, e to the e, now we have to remember, sometimes e throws us off, but e is a constant. And so if we've got a constant to a constant, that's, again, that's derivative of just a number, right? So derivative of any constant is 0. So that would be 0. The e to the x derivative, that one was just e to the x. So we have to remember that one. Now as we look at the next one, x to the e. So compare that to, remember e being a constant. If I were just doing the derivative of x to any other constant, I would be using that power rule, right? So if I was doing the derivative of x cubed, then I would say that's 3x squared, right? So same idea here, it's just that we have an irrational number as our exponent, but it is just a constant. So I would bring it down, just power rule. So e times x, and I have to take one away from e, which we can't really do without, we can't, this is 2.7 and it keeps going and going, so we have to just leave this expression e minus 1 as the exponent. Now with the last one here, if you have an expression with a variable as the base and the exponent, that doesn't really work for our power rule. Here we had, a numerical base, we had e. Here if we have a variable to a variable, we don't have a method for that at this point. And so this is where, so here it says in part D, that's problematic because using differentiation rules that we know we can't, there's nothing that we can use there. So whenever a variable appears in both the base and the exponent, we have to use a technique called logarithmic differentiation. So I guess we just wrote a similar thing here. We had x to the 2x. So let's just take a look at that. So what we would do here, we would take the log of both sides of the equation. Now typically you're just going to take the natural log. That's the easier one, because the e's appear quite a bit in here too. Natural log is the best one to use. So if I would take the natural log of both sides of this equation, okay, so I'm just taking ln of y on this side, ln of x to the 2x on the right side. Okay, now we did do some work with logarithms in the previous unit. There are some properties of logarithms that we can use that don't even involve derivatives yet, but if you remember, if you have a log of something to a power, that power can get multiplied, and that's not a derivative, that's just a property of logarithms. If you have ln of x to the 2x, you can write the same expression as 2x times ln of x. So we're going to rewrite that. So this logarithmic differentiation is useful because you get to apply some of those log properties, which allow you to write simpler expressions, but equivalent expressions, and it makes it a little easier to do the derivatives at that point then. Okay, so now what we're going to do, we can take the derivative of each side of this equation. So on the left side, and we're going to do the derivative with respect to x. Okay, so because on the left side of the equation we have ln of y, that's just going to be 1 over y for the derivative, but remember, dy dx has to follow because it has the variable y rather than x. Okay, so this is where the implicit piece kind of fits in there. Now on the right side of the equation we have 2x times ln of x, so that's a product, 2x times ln of x. So we're going to go derivative of the first times the second, which is going to be 2 times ln of x, plus the first, 2x times derivative of the second, which is going to be times 1 over x. Okay, and then if I continue on here, so I've got 1 over y dy, I'm just going to recopy that, dy dx. And over here, I'm going to have, if you look at this, 2x times 1 over x. Well, the x's are going to cancel. I'm just going to have a 2 there. So I'll have 2 ln of x plus 2. Okay. And then to solve for my derivative, I just need to multiply by that y over to the right side of the equation. So dy dx is going to equal y times this expression, 2 ln of x plus 2. And then typically what you do on these, rather than, if we can write everything in terms of x, that's usually what you'll see for your answer choices. So because we know y is equal to x to the 2x power, let's substitute that back in right here. So dy dx equals x to the 2x times this expression to ln of x plus 2. And that would probably be the way we'd leave our answer in that. Okay? So that's an example of logarithmic differentiation. All right, so let's take a look at the next one. So it says, think about how you would take the derivative of y equals 2 to the x. Now we did these before, where we had, when we did the derivative of e to the x, we also did the derivative of like numerical bases, like 2 to the x. And there was a formula that where it was just 2 to the x, but then you had to go times ln of 2. It says you could use logarithmic differentiation, and then you wouldn't have to try to remember this formula, how that goes, because what you could do, just like what we did up above, we could take ln of y equals ln of 2 to the x, and then we could multiply that 2 down, or sorry, the x ln of 2, and then now we can do the derivative of each side of the equation, and so I'd have 1 over y dy dx, and then on the right side, this is just, ln of 2 is also a constant, and so when I do the derivative of ln of 2 times x, it's just the x disappears, right? Because it's like if I took derivative of 2x, it would just be 2, but ln of 2 is a different constant, but it is a constant, and so the x would disappear. I just have ln of 2 there, and then so my dy dx would equal y times ln of 2. Well, my original y was 2 to the x, so it would be 2 to the x times ln of 2, which is what the formula tells me. But sometimes we forget, and I forget those formulas too sometimes. It's nice to have a different way to, come about that answer if you can't remember exactly how the formula goes. Okay, so that would be what we'd have for that one. And then for the last example here, I kind of left it worked out just to talk through it and save some time here. But, okay, so here, usually they'll tell you, use logarithmic differentiation. This one would be kind of a beast to do without, we'd have to do a quotient rule, which would involve, the power rule on top with I guess chain rule wouldn't apply too much there, but on the bottom, definitely chain rule would apply. You'd have a couple chains to deal with there. So sometimes they'll just say, hey, use logarithmic differentiation. And if you do have like a complicated expression, especially a fraction like that, take the log of both sides. So if I do ln of the left side, ln of the right side, this allows me, what the log stuff allows me to do is to apply those properties, and then it makes it become much simpler, because if I have a ln of a quotient, remember those rules say I can take the ln of the numerator minus the ln of the denominator, and now in there I've got these powers which are able to get multiplied down in front. Now keep in mind I haven't done any derivatives yet. I'm just rewriting these expressions, or at least the stuff on the right side of the equation. I'm just expanding that using log properties, right? So that 2 comes down, goes here, this 1/2 comes down, and it goes in front of this expression. And now at this point, now in this row, I'm ready to start doing derivatives. So derivative of ln of y is 1 over y, and then dy dx. Okay, over here, the derivative of ln of 1 over, or the derivative of ln of x minus 2 is 1 over x minus 2. And then that 2 was already there, so that stays in the numerator. And then this piece too, derivative of ln of x squared plus 1 is 1 over x squared plus 1 times the derivative of that, which is 2x, so the 2x is in the numerator, right? Remember, the derivative of ln of u is like u prime over u. The u prime piece is like your chain rule piece, or you could say it's 1 over u du, but that du, derivative of u, this being x squared plus 1 being the u, ends up back in the numerator, okay? So there's your u prime over u, or du over u. This 1/2 is still there, right? Okay, so now if I simplify this a little bit more, this 2 and the 1/2 would cancel the 2 and the 2x, so I just have an x up there. So now I've got this expression right here, and I would probably multiply this y over here at this point, so the y gets multiplied by the whole right side of the equation. And then finally, replace y with the original expression here. And we don't have to do, any more simplifying than that. We can probably just leave it just like this, okay? But the idea, yeah, take the ln of both sides, and then you do have to expand using your log properties. And then once you've done that, that makes the derivative part much easier. Okay, so that's all for this video.